We tend to think of life as sunny, even on Earth. But out of our solar system's many potentially habitable worlds, most are probably like this, shrouded in ice and darkness, with the only light coming from chemical reactions powered by heat deep below. What if life isn't rare? What if life is everywhere? Imagine oceans hidden beneath ice and salty slush, glowing not from sunlight, but from heat deep below. Imagine chemistry rich enough to power life, trapped under kilometers of frozen rock. These are not fantasy worlds. They are real places inside our own solar system, and any one of them could be home to life today. First, Enceladus. This moon of Saturn wows us with icy geysers erupting from fractures near its south pole. Plumes shoot 300 meters high and 25 kilometers into space, leaving trails of vapor and ice crystals. When Cassini got close, it found the plumes contained water vapor, organic molecules and tiny grains that hint at hydrothermal activity on the ocean floor. The cracks or vents release warm water from the seafloor, creating chemistry that could support life. In the nooks and crannies around black smokers on Earth, you find ecosystems thriving on sulfur and other compounds seeping from vents. And that's just from the sun's rays. If there are vents on Enceladus, they could provide energy, heat, and chemistry. That's exactly what microbes need to survive. No wonder scientists call its plumes one of the easiest places to sample an alien sea without landing. But what if we find nothing on Enceladus? There's always Europa, Jupiter's moon with a cracked, wandering ice shell hiding a deep global ocean. We know this because magnetic data and surface features point to vast liquid water under the ice. Scientists think that Jupiter's gravity is kneading the moon's interior, creating heat and possibly hydrothermal systems on the seafloor. Kneading also keeps water from freezing solid, even though it's just 150 kilometers from Jupiter. That tidal heating keeps the surface ice layer thin, and according to models, it can punch holes through the ice shell, allowing water from the deep ocean to reach the surface. Saturn gave us a plume example. Jupiter gave us a moon with a vast global ocean, an entire world-sized aquarium kept liquid by tides. If microbes ever arose on Europa, they could still have a place to live right now. But what if both Enceladus and Europa are dry? Next up is Ganymede, Jupiter's largest moon, which has its own magnetic field. A protective bubble like this could shield internal habitats from cosmic radiation, allowing life to survive. And there is strong evidence that Ganymede contains not one, but multiple layers of liquid water trapped beneath different ice shells. A big, protected ocean with layered chemistry drastically increases the chances of varied environments. More chemistry means more ways life could exist. What if Ganymede's oceans are dry too? Titan is next, Saturn's largest moon, which looks alien on the surface. Lakes of liquid methane and skies rich in organics. But below that hydrocarbon skin lies another possibility, a water-ammonia ocean beneath the ice. Water mixed with ammonia could stay liquid at lower temperatures, and the surface showers Earth-like organic molecules down into the ocean. Instead of sunlight, Titan's hidden sea would get a steady feed of complex organic material, a prebiotic smorgasbord. That mixture of water and organics is exactly where chemists say life could start. Finally, what about Ceres? This small world in the asteroid belt that surprised everyone. Bright salt deposits, occasional water vapor plumes, and minerals that form in watery environments hint at a subsurface system of brines beneath its crust. The Dawn probe returned images of cryovolcanic features and hydrates. A dwarf planet with pockets of salty liquid and an internal heat budget means microscopic habitats could exist in pockets protected from harsh space conditions. Of course, we can't forget Mars, the planet that seems most like Earth. The surface is harsh, but radar and chemical clues point to underground saline pockets, transient brine flows, and deep aquifers protected from radiation. If life went underground when the surface dried, it might be surviving in cold, salty niches, fed by chemical energy rather than photosynthesis. Modern probes and radar studies keep uncovering hints that Mars may not be lifeless. It may just be hiding its life beneath the dust. Why does subsurface life matter? Because these environments are stable. They are insulated from radiation, buffered from temperature swings, and they can host energy gradients, the engines of metabolism. On Earth, subsurface microbes live kilometers below the surface, surviving on chemical energy alone. That proves life can persist in the dark. So where should we go first? Sample Enceladus's plumes, send a lander to Europa's chaos regions, peer under Titan's ice, study Ceres's bright deposits, and drill shallow on Mars. Each target teaches us something different, and each one brings us closer to answering the single question that changes everything. Are we alone? If this opened your eyes, leave one word below naming which world you'd explore first. A small like helps others find this video, and subscribing means you won't miss our next deep dive into the missions that will test these ideas. The search for life is no longer science fiction. It's the next decade of exploration.